Hello guys, today I'll be talking about exactly what BlackBody radiation is. So, you can just assume that you have a box, right? Oh my god, this is horrible. Yeah, you can assume you have a box and that the exterior of the box has atoms in it, and you can treat each atom as a harmonic oscillator, right? So, essentially, if it's a harmonic oscillator, we know that harmonic oscillators they vibrate and atoms, which I'm assuming it's the harmonic oscillator, emits light. And since these atoms emit light in a perfect black body, the emission and absorption are exactly the same. That's why, and the idea is that since harmonic oscillators can only emit light with certain frequencies in a perfect black body, the emission spectrum is basically continuous. You can emit any frequency of light, and that it's a perfect black body, meaning that the emission and absorption is contained within uh, the box, right? So this is a continuation of the black body thingy lecture pseudo that I had. So in a black body, you have, since like I said, the modes of light is being emitted and it's being contained within the box. You have a standing wave, an electromagnetic standing wave, and you have different modes of oscillation within the wave, right? But as you know that the box is 3D, so it has uh, more like a three dimensional modes of oscillation. So as you can see in this equation here, there's an nx, there's an ny, there's an nz, and there's in each has a corresponding k vector, right? So given that each has a corresponding k vector, what we want to know is the number of modes as a function of frequency. So in a given frequency interval, we want to know how many modes exist, right? So what we can do is that we know that the 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 wavelength here is proportional to 2L over nx, ny, and z. So which means there's a surface boundary in which it's constant wavelength, i.e. constant frequency as well. So so given that we have an octant of a circle, which in which case, and the octant is composed, the dimensions are nx, ny, and nz, and it's discrete, meaning that ny, and z are discrete values, right? And if we take the volume of this, we can get the number of modes that would exist in that volume. As you can see, if you have discrete values, uh, taking the volume of those discrete values will give you the total number of modes, say, that can exist in that volume. So, given that this n value here is just a radius, and it's composed, and the value is just the square root of nx, ny, and nz, the square root of those quantities squared. So, if we know that the fundamental frequency, given the dimensions of the box, if the dimensions of the box has L by L by L, that the fundamental frequency is NC over 2L. And so we can calculate the volume of the box, 4/3 pi n cubed, divide by 8 because it's an octant. So the volume would be pi n cubed over 6. Knowing that the fundamental frequency is NC over 2L, we can substitute for n and get 2L or 2L times F over C and plug that back into this equation to get the volume. And the idea is once we do this, we can find what the differential volume would be by taking the derivative of uh, the quantity that I've described, and taking the derivative of that, you get. So as I mentioned in the previous video, the number of modes between a frequency f plus fdf is just equal to 8 pi l cubed f squared over c squared times df. So that means the volume, which is just L cubed in this case. So if you divide by L cubed, you get the volume. So you get the density, how many modes you can have for a given volume, and that is just equal to 8 pi f squared over c squared. And so what we need to know is what the average energy is per mode, and that's just equal to kBT. And the only way you would have known that is, well, I'll just describe this really quickly as quick as I can. If something is in equilibrium, that means that the number of particles per given energy state is approximately the same. So it's just equal to this factorial where these are the energy boxes you can have, and the number of arrangements of the particles within the number of ways you can arrange the particles is given by this quantity. And from there, if you just use the Stirling's formula seen here, you can, under the constraint that the probability of all energy states is equal to 1, sum of all the probabilities, and that, and if you also constrain the energy, use Lagrange multipliers. This is not really that important, so if you don't get it, it's fine. And you basically get the partition function. And what you can get is that since you can treat the atoms as harmonic oscillators, you can find out what the average energy would be for a given mode. And using this formula, using this partition function, if you just want to know, if you're curious, you can just look this up. You can just plug it into the formula, and knowing that the average energy is just d log of the partition function divided by d beta, which is just 1 over kBT, then you get the value you get for the average energy is just kBT. And that's just for one mode of oscillation. And there's like a lot of modes of oscillation. So if I multiply this density by kBT, this is equal to, this was from the Rayleigh's formulation, I think, if I don't have his name wrong. So, which predicts that if you integrate this to get what the energy would be, if you at very high frequencies, basically this just jumps to infinity. So the distribution, it would have looked like this for a given frequency, but the classical prediction is this. This is experimental, this is classical prediction. And you can see here at low frequencies, the prediction is, fairly correct, but then as you go to high frequencies, it just goes to infinite. The energy density just goes to infinite, which means this prediction is not correct. And the correct prediction the correct prediction came from Max Planck's equation thingy, saying that energy is proportional to his constant times the frequency. And this regime is explored accurately if HF is much greater than kBT of whatever your system is. And so as you can see here, treating E is equal to HF, you can calculate the average energy to be just using this formula. It's just geometric series and stuff, that it's equal to, in the classical limit, as you can see here, it's proportional to kBT, and for in the quantum regime, it's proportional to this value there. And from there, you can just integrating over the energy density, you can get Planck's distribution. And this is where I'm gonna stop because I'm tired and I don't want to talk anymore. Yeah, that's it.